So, OK, what I'm talking about for today is I'm trying to introduce factorization algebras, which are also known as chiral algebras. There's a book by Bailenson and Drinfeld on this subject that's relevant to these purposes. And also just a general combinatorial pattern that I'll talk about to some degree, which is called factorization. And I'm also going to try and give the yoga of the thing and explain to some extent why anyone cares. So yeah, so the kind of prehistory to the idea, or a way that you could just invent it by yourself if you gave it some thought. So if you have a point in a curve, there's some notion of what's called the affine Grassmannian. So it appeared already in the conference. It's meant to model. Sure. Thanks. OK, so it's meant to model the set of points g of kx mod g of ox, where kx is the field of Laurent series at x. So and ox is the set of Taylor series. And so this means the kx points of G mod the ox points of G. So the affine Grassmannian is a great thing in geometric representation theory that we'll say a lot about during this week. So this, unfortunately, isn't quite a precise definition. It can be made precise, but an easier definition is to define it as a pre-stack. So I have to tell you what its S points are. And it's the set of consisting of a G bundle on x cross S with a trivialization on x minus x cross S. So one way to reformulate this, just so that it's more obvious that its k points are given by that particular set, is to give a definition that depends less on, that doesn't depend on the actual sort of global smooth curve that we've chosen. So another definition, just it's not so relevant to factorization necessarily, but just because the affine Grassmannian is being introduced now. Another perspective is to define dx to be the spectrum of this algebra. So I'll call this the disk. I will call this the punctured disk. So this is spec of k double brackets t. And now I can try and say words like, replacing x by the disk here, but that would be slightly bad. Well, it would give the wrong answer because this product with k double brackets tx would give the wrong answer. So the right way to say it is to replace everywhere. I can say dx sub s is spec of a double brackets tx. Punctured disk at s is going to be spec of a Laurent series with coefficients in tx, where s is equal to spec a. And then redefine the affine Grassmannian G x, I'll write a prime for a second, to be the set of G bundles. Well, it's a certain pre-stack. Its S points are the set of G bundles on this dx sub s with a trivialization on dx, on the punctured disk. So yeah. So OK. A word about this formula. So we certainly know what this formula means when A is a usual commutative ring. If you want to understand it for a derived ring, you should take the projective limit of A tensor with k adjoined tx mod tx to the n, projective limit over n's. And then you obtain this algebra by formally inverting t, which makes sense in the derived setting. So there's a clear map like this. And the fact that it's an isomorphism is FP-QC descent. And people often call this the Bouvier-Laszlo theorem, which is just a helpful way of organizing the notion of what's going on. It doesn't follow so far from FP-QC descent. OK, so great, that's the affine Grassmannian. Oh, and in this picture, you can easily see that its k points are, well, the set of points I said. Namely, like every G bundle on the disk is trivial, so you choose some trivialization. And then you're given a second trivialization on the punctured disk, so that's an element of G of k. But there was some redundancy because we chose a trivialization, and that you mod up by that to get G of k mod G of O. OK, so the way factorization emerges is when you try to look at just the natural ways of generalizing this picture. Valenson and Drinfeld notice that this generalizes. So the first thing they noticed is that there's a version of the affine Grassmannian that lives over the entire curve x. So what they did is they constructed a space G big X, that's difference in notation, that maps over x. And it's a sort of generalized fibration that has fibers. So I'll give the definition in just a second. It has fiber G little x at a point x and x. So namely, again, I'll define it as a pre-stack. So first of all, the fact that it maps, of S. OK, so now the fact that it maps to x means that part of my data here has to be some map from S to x. So I'm going to call that map little x. So I think of it as an S point of x. Plus the data of a G bundle on x cross S. And then what we want is we want to say a trivialization of this G bundle on x cross S away from the point x. So what does that mean as the point varies? That means a trivialization on x cross S minus gamma x, where gamma x is the graph of the map x. So it's some copy of S that lives inside of x cross S. So here, gamma x is the graph of the map x. OK, so that was their first observation, is that this affine Grassmannian can be made to move continuously over the entire curve. And already it's a kind of nice feature that you couldn't do in number theory, because you can't move primes.
Excuse me, may I ask a really strange question?
Yeah.
Why is it called affine?
It's kind of convoluted. So So this affine Grassmannian, you can kind of think of it as an analog of G mod B, but it's infinite dimensional. So it's an in scheme. It has something that looks like a Schubert stratification, but it keeps going. And if you generalize this picture slightly,
It is the Grassmannian for the affine algebra.
yeah, it's basically the Grass, or
The origin of the name.
Right. But you can still ask what's affine about it. It's more like the affine Weyl group. The affine Weyl group is the analog of the Weyl group in this picture. No, it's because the relevant Weyl group is the affine Weyl group. It acts by affine translations. All right, it's a word. Affine means referring to this kind of infinite dimensional geometry with g of k. OK, so the first thing that Beilinson and Drinfeld noticed is that you can take a point x and move the affine Grassmannian continuously over it. Then the next thing they noticed is that actually, given any integer n, they can define some version of the affine Grassmannian that actually lives over the nth power of the curve x. So how does that work? So again, I'll define it as a pre-stuck. So now what we have is a map from we have a map from S to x to the n. In other words, we have an n tuple of maps that I'm going to call xi. Then, no surprise, it's a G bundle on x cross S. And now what we do is we say with the trivialization on x cross S minus the union of the graphs of the map xi. So I'm going to, in the setting when I call the collection of maps xi by x, I'm going to use gamma x to be this union of graphs. So how does this? Well, so a fact is that, first of all, Gurji x to the n is an n-scheme. In fact, it's even a classical n-scheme by the theorem of Dennis and Nick. So it means it's a union of classical schemes. So in principle, from this definition, it could not be classical, but good news, it is. What was that? Classical scheme, non-DG, yeah. So OK, so it is an n-scheme. And how does this thing look? So let's say n is equal to 2. So we understand the n equals 1 case. The fibers just look like copies of the affine Grassmannian at the given point. So for n equals 2, what's the fiber at a point xy? So there are two cases. So the first case is that x is equal to y. And in this case, what are we saying? So we're saying, like, you take the union of the graph of this map x twice and remove it from x cross s. Well, that's just the same as removing, like, the graph of the map x, right? There's, that union doesn't change the complement. So in this case, we're just giving the same definition that we gave before. So this is just Gurji x. Any questions about that? So the second case is also easy, but maybe requires slightly more thought. So if x is not equal to y, then what you get is the affine Grassmannian at the point x crossed with the affine Grassmannian at the point y. So
do you want to say disjoint disjoint?
Well, I'm just a simple man with points, fibers at points. Is that OK, so in the case that x is not equal to y, what's the proof? So you just cover x with the two open sets x minus x and x minus y. And then what this fiber, sort of Gurji x squared, like fiber at xy, what this parameterizes is supposed to be a G bundle on X with a trivialization on X minus X comma Y. So I can reformulate a G bundle on X as a G bundle on X minus X and a G bundle on X minus Y, identified on X minus XY. So this is the same as G bundles on X minus X. So I'll give them names, P1 and P2 on X minus X and X minus Y, with trivialization, like each with trivialization on X minus XY, just by descent. And, well, the good news is that now, since these points are different, giving a G bundle on X minus X with a trivialization here is the same as giving a G bundle on X with a trivialization away from the point Y. So with a trivialization on X minus Y is the same thing as a G bundle on X minus Y, no, X minus X, with a trivialization on X minus XY. Just because these points are different, like in this first picture, the bundle is trivialized in like a neighborhood of X, and therefore, like, it doesn't have anything to do with anything. So you apply this to each of your open covers, and you get that product description.
Before you erase this, this all is happening formally, like S there is a derived step. It's a derived affine scheme when you define it, or not, or this is not.
It does. It's not so relevant. So if I want to make a careful distinction between derived algebraic geometry and classical algebraic geometry, I will. But otherwise, it's. So the words. OK, if I say something that only makes sense in classical algebraic geometry, I'll say so. But otherwise, you either can interpret it classically or derivedly, and when you need to make that distinction.
How you do that complement thing? It's just like how you formulate this kind of
There's a procedure of, well, there's a procedure of removing.
It's enough to define your functional point on non-derived.
No, but that I don't want to do that. OK, so there's a notion of trivial G bundle in derived algebraic geometry. So if G bundle is a map to point mod G, this is the map. This is the lift of that map to the point mapping to point mod G, and there's a way to remove closed subschemes. OK, so this is the affine. Well, this is what happens in that case. So more generally, it's convenient to reorganize, to repackage things. So I'm going to use the following convention now. Instead of x to the n, which I used for combinatorial simplicity, if I is a finite set, then I define ∇g, comma x to the I, so that if I is the set 1 up to n, we get our earlier thing. So in other words, it's an I tuple of points, so one point for each element of the set I, a G bundle on X, or an S family of G bundles on X, with a trivialization away from the points xi, from the union of those points. So it doesn't depend on the ordering in this thing at all. So then it's easier to say what the combinatorial pattern is that the affine Grassmannian satisfies. So the first thing to note is that it's going to be kind of formal, and then I'll explain it. At least. So if F is a surjective map from I to J, there's a diagonal map delta sub F from x to the j to x to the I. So how does it work? Well, if I have some bunch of points x sub j, then I'm supposed to assign to like every element I some point of x, and I take x sub f of I as my coordinate in the place I. A slicker way to say this is that x to the I is the set of maps from I to x, and we're just restricting along this map. Well, OK, it's the set of maps from j to x, restrict along this map. So we can reformulate our first condition as a certain axiom. So condition 1, which I'm going to call Ran's condition. This is the same Ran who appeared in Dennis's talk yesterday. Ran's condition says that for every surjection f from I onto j, if you form the affine Grassmannian over x to the I, this maps to x to the I. Oh, poor board space. OK, then I can diagonally embed my x to the j. And this fiber product is going to be ger g comma x to the j. So this is Cartesian. So this is what we saw in the case when n was equal to 2. What we're saying is that if you have 2 points on the diagonal, then the fiber of the affine Grassmannian at that point in the diagonal just looks like the sort of corresponding affine Grassmannian at that single thing. So that's axiom 1. Well, it's not an axiom, it's a property, but the second axiom is going to be, there will soon be axioms, factorization. And what this says is that every time you have a decomposition of the set I as two disjoint sets, I1 and I2, then you can play the following game. So first of all, you can define a certain subset x to the I1 cross x to the I2 sub disjoint. This will be an open subset of x to the I. And what is it? Well, first of all, in the example when n is equal to 2 and we're taking the main diagonal, this is just going to be the complement to the diagonal. In general, this is the open set of coordinates. So I can think of a point as a bunch of, as a pair of like xi for I and I1 and xi for I and I2. Maybe I'll write xj. And my requirement is that x to the I1, x to the I is not equal to x to the j whenever I is in I1 and j is in I2. So easy to make sense of this scheme theoretically as an open set. But for example, its k points are the ones I just said. And then what the factorization condition says is that, so for example, if n is equal to 2, I'm saying, and this is the main diagonal, I'm saying you have a pair of points and they're required not to be equal. So what this factorization condition then says is that if you take x to the I1 times x to the I2 disjoint inside of x to the I, and then you take the affine Grassmannian mapping over this x to the I, then I can form the fiber product of right here. And what the fiber product will be, I claim, is x to the I1 cross ger x to the I2. And this should be restricted to this open set, certainly, since this thing maps to x to the I. So sorry. So this is just the restriction of the product to that disjoint locus. OK, so I want to spell out for a second that this is like a slightly weird picture. So it's not unreasonable to think that this affine Grassmannian is smooth in some sense over x to the I. And what you have is like a kind of smooth family where the product of some variety with itself is degenerating to the variety itself. And for example, that's not possible in usual algebraic geometry because the dimension jumps. But here it's an infinite dimensional variety. And luckily, infinity plus infinity is equal to infinity. And yeah, so OK, so
the map is actually smooth? Grassmannian towards
it's formally smooth.
Oh, okay.
Yeah. Any questions at this point? OK, so there's one more observation. So a quick definition is that a D space, or equivalently dx space, is a prestack over x to rom. Or whatever. Or sometimes the phrase is used for the thing that you obtain when you pull back to x. So you might say like y over x is a D space if someone has told you some D space over x to rom that pulls back to your given space. So my claim is that the affine Grassmannian canonically has this structure. In other words, it canonically descends to live over actually x to the I de rom for every I. So Gurgi x to the I nicely, so these words will be made more precise, descends down to x to the I de rom. In other words, what that means is that I can define Gurgi x de rom to the I over x de rom to the I that fits into a Cartesian square like this. And how do I do it? So we just, again, imitate our same definition. So giving an S point of this prestack.
So this is existence of such Cartesian diagram is the claim.
It is the claim, but it's more than just existence. I want to give it. It's not a mathematical claim; it's a construction. So, nice is something that needs to be justified later. OK, so we play our same game. So first of all, we want to map from S to x to the I de rom. So that's just the same as an I tuple of maps from S reduced to x to the I. Oftentimes people, if you're taking S to be a derived scheme, they write classical reduced. I personally find that redundant. So it's a map from S reduced to x to the I. It's a G bundle on x cross S. And it has a trivialization on x minus x cross S minus the union of the graphs xi, where now, note, the maps xi are like, these are certain reduced schemes, right? It's the graph of the map from S reduced to x to the I. But that still lives inside of x cross S. In other words, what I'm saying is that when you take this, OK, what's the formal structure of the definition of the affine Grassmannian? It's you have a point, you have a G bundle, and then you have a trivialization on some open set determined by that point. And what I'm saying is that that open set only depends on the point restricted to S reduced, because we're just taking the complement to something, and complements only depend on the reduced structure on that thing. So this is perfectly well defined. And what I just essentially explained is why, when you pull back to x to the I, you get the old affine Grassmannian. The G bundle is on x times s, right? But see, like, what does it mean to give something in the fiber product? That means that giving something in the fiber product here means I've extended my map from s reduced to x to the I to a map from s to x to the I. That's the only thing an extension means. So I want to get back my original definition as soon as I've extended my map from s reduced to s to x to the I. And so that's why it has to be this way. OK, so sorry?
So on classical schemes, the values are stupid, right? Because they have to stay in a single point. Or the values are...
It behaves exactly the same way for derived and for classical schemes. Like you would be hard pressed to come up with a statement true in classical algebraic geometry about this that would be wrong in derived algebraic geometry. So. Yeah, everything is true for S derived. OK, so a claim, or not even claim, is that these certain spaces satisfy the same axiomatics. You just replace x to the I everywhere. By x Derived to the I. So the factorization still works, and the Ran condition still works. It's just that now you're over x to the I Derived. So, and you take that open set Derived, everything in sight Derived. So they commute. They commute. Because, OK, they commute. Dennis, time. Great. OK, so axiomatics are that a factorization space over x is an assignment that sends every finite set I to some pre-stack y sub x Derived to the I. It's a pre-stack with a map to x Derived to the I, and satisfying our earlier axiom. So and these two sets of axioms should satisfy various compatibilities. Essentially, what it says is anytime you produce two spaces over something and they have two different isomorphisms between them forced by these axioms, those two isomorphisms should be the same. So there are various examples of factorization spaces that come in sort of local geometric Langlands. A basic principle here is that if you write a formula for a very vague principle that will be made more precise during the tutorial is that if you write a formula for something using only the disk and the puncture disk, then it should factorize. So in the case of Affine Grassmannian, it was a G bundle on the disk with a trivialization on the puncture disk. So you expect it to factorize. OK, so any questions before I move on? Sorry? Anywhere. What? It's an executive decision. Next. So, OK, so the next idea is factorization algebras. So these are equivalent to something called chiral algebras. Actually, I'm not defining anything.
Oh, wait a second. So they're setting like the Grassmannian is a factorization space like without the deriveds.
It is a factorization space with the deriveds. So that's what the claim here is.
Yeah, but if I remove all the deriveds everywhere.
Then it makes perfectly good sense to talk about factorization space over any pre-stack.
Right.
It's factorization space over. I just wanted over x to mean over x derum, really, for simplicity, because that's what we're going to use in practice. Any other questions? OK, so the idea of factorization algebras is that you want to linearize the notion of factorization space. For example, you want something like the cohomology of a factorization space to be a factorization algebra, in the sense that cohomology linearizes geometry. So the definition is not so far from here, then. So first condition is that, so a factorization algebra on X is an assignment that we just imitate these axioms. So every finite set I goes to some a sub x to the I, which is a d module on x to the I. So I'll write d of x to the I, but this is what everyone else has been calling d mod of x to the I. And these should also satisfy various axioms. So one axiom that this satisfies is that so they're exactly parallel to before. So the Ran condition says that every time you have a surjection of finite sets from I to j, you can again take this diagonal map. You can Schriek restrict, because that's the only thing available to you in general, this a sub x to the I. So you Schriek restrict it to, now it's a d module on x to the j. And what you want is an isomorphism in here. And the second condition is the real factorization axiom, which says that if you have I equals I1 disjoint union I2, then when you restrict a sub x to the I, so I'll just write restrict because it's star is equal to Schriek here. When you restrict this to x to the I times x to the j, take the disjoint locus, you should specify an isomorphism between this and a sub x to the I1 times, exterior product, a sub x to the j, also restricted to the same locus. And again, these should satisfy various compatibilities, which in this case say that anytime these axioms force two isomorphisms between two different d modules on two somethings, then those two isomorphisms should have been the same. OK, so an example is the rule that attaches to every finite set I, the dualizing sheaf on x to the I. Because whenever you Schriek restrict the dualizing sheaf, you get the dualizing sheaf. So everything in sight here is, and whenever you exterior product two dualizing sheaves, you get the dualizing sheaf. So everything in sight here is a dualizing sheaf. Another example is that if you have some if you have some nice factorization space, a nice factorization space. So this means lots of things should be in schemes. In particular, I'm really thinking of the Affine Grassmannian here. If you have some nice factorization space, that implies that what you should properly call Borel-Moore homology of Y forms a factorization algebra. So better way to say it is that we have these maps pi sub I from Y sub x duram, or I'll actually just write it like this, to xi, and you take pi I upper shriek of pi lower star duram. Actually, I don't need that. You take a finite set I to this D module on x to the I, the one you obtain by taking Duram cohomology of the dualizing sheaf on Y, which classically goes by the name Borel-Moore homology. So one example is that for the space, for like the affine Grassmannian, it's what should properly be called homology, because the affine Grassmannian is ind proper for a reductive group. And this particular factorization algebra is very important in the work that Dennis and Jacob are doing on the Tamagawa number. In the case of the affine Grassmannian. This map? So it would be for the affine Grassmannian equaling Y in that case. So this is exactly what I mean, that factorization algebras are a linearization of factorization spaces. So this kind of thing, like if you have some factorization space and you do something to it, then you'll end up with a factorization algebra. Maybe we'll see more examples of this during the tutorial. OK, so a question is like, what are these things? So like, who cares about factorization algebras, about factorization? So let's try and think out what the axioms mean for a second. So brief heuristic is, OK, so personally, when I think about a sheaf, really, I think about its fibers. I'm just not capable of thinking about the whole sheaf at once. So the first thing I want to do is look at what are the fibers of these sheaves. So what I gain is that given any finite set of points x sub n in x to the n, I can take the fiber of my sheaf, the fiber at these points. So namely, it's like take my D module on x to the n and just take the fiber at the corresponding point here. So the first observation, which is the Ran observation, is that this only depends on the corresponding subset x1 up to xn inside of x to the n, inside of x. So what's the difference here? So here, if n is equal to 2, I allow the point xx, and then I'm taking the fiber. But what my Ran axiom says is that that's the same as taking the fiber of a, just like ax at the point x. Sorry, too many x's. But I'm saying, like, any way you write this set with some multiplicities and consider it inside of some power of the curve, if you take your fiber of your sheaf there, you'll get this thing. And now what does the factorization condition say? So what factorization says, and actually I want to say you can think a little bit more vividly about this. So what you're allowed to do in this world is, OK, when you think about a sheaf in terms of its fibers, you think it's some vector space that kind of varies continuously with your point inside of your space. At least that's won't be too harmful. So it's some continuously varying vector space. So in this case, I can continuously vary my points in the curve. And what that's showing here is that I can continuously vary these points, and I can allow them to collide. And again, my vector spaces are supposed to be continuous with respect to that, just because I can allow them to collide onto the diagonal inside of x to the n. So So it only depends on this. And what I'm getting are vector spaces x1 up to xn that are continuous with respect to varying and collisions. What was that?
When you collide, are they like?
It just looks like
Will it be an actual local system on?
Typically not, very rarely. Yeah, I mean, like in the case of omega, it is a local system, but that's about all you're going to come up with. Okay, so right, and then what the factorization says is that when I take this point a sub x1 up to xn, this is equal to the tensor product of the vector spaces a sub xn. So for me, this looks a little confusing looking at the conditions, because like, what am I saying? So it says, like, OK, I do all this fanciness with finite sets, but then I see it really only depends on what happens with a single point. So if I just think about the fibers at points, it's really boring, because it's just the tensor product over the like sort of the points in my set, but counted without redundancy. So at x, x, y, you just take the tensor product at x and at y. And so that's kind of confusing. Like, why do I need to specify all of this extra data at these fancier points, like these fancy subsets of x? And the answer is that what's really going on here is that, like, what you can think is that, so this is a heuristic that will be made more precise, is that the assignment of just a single point in x to this vector space a sub x is local. So this is purely local. So like, I mean, OK, these things are, they're algebras, they're not spaces, but like the affine Grassmannian, it really depends just on the point x. Like that's what you study in local geometric Langlands. And then the extension to factorization is about like specifically extending to the case of these finite sets and allowing collisions. And then what this factorization condition says is that the thing you obtained is still somehow purely local. Maybe less purely local than it was before, but at least its fibers only depend on really local data. And then the extension to factorization, what that buys you is, so this hasn't been justified at all, but it allows you to do local to global procedures. It's not true, because you have a collection of D modules. So I know. But what I would formulate it slightly differently. So what you can think is that you have this huge collection of D modules. And what the first one, the one over the power of the curve, encodes is the purely local information. And what the ones over the higher powers of the curve, like the information they contain as points collide, it's the data that lets you do local to global. So it's hard to really say what that is in classical terms of like harmonic analysis, because you can't let primes collide. But it's some extra thing that lets you perform that.
Is it so that you can reconstruct a factorization algebra from the neighborhood of the diagonal?
I don't know what that means. So it's something on each x to the I.
Restrict just to x to the I near delta. All the data.
Yes. OK. Let me say no. So you have to be careful. So for example, like if you were over the second power of the curve, the formal neighborhood of the diagonal, its de Rham space is like a D module on that formal neighborhood is the same as a D module on x. So you've forgotten what happens away from the diagonal. But it's not a horribly wrong picture either. OK, so this is the major idea. So it's this factorization geometry. So I want to say we won't necessarily use factorization algebras. Well, they'll appear, but we won't need them too much. But see, the fact is this factorization condition will justify some local to global principles that will be appearing. So it's a way of spotting when local to global principles should be relevant. And it also occurs frequently, like you really use the algebraic structures at your disposal to prove a lot of the theorems that we're going to be talking about. So I want to just give one final repackaging of things, which is in line with this heuristic. Any question? OK, so one game we can play is, OK, so this will be a repackaging, but it'll only be a repackaging of Ran's axiom. OK, so what we know is that, so what does Ran's axiom say? Ran's axiom says that we're given so I'm going to write f sub x to the I to emphasize that it's not an algebra, it's just some sheaf. So what Ran's axiom says is that we have an assignment for every finite set I of some D module here. And every time we have a surjection, I onto j, we're given an identification of f sub x to the I, delta f upper shriek, with x to the j. Whoops, f sub x to the j. And I'm implicitly requiring the cocycle condition. So in other words, this assignment of I going to f sub x to the I forms a compatible system of D modules in this sequence of categories d of x to the I. So what I'm really saying when I say forms a compatible system is that the data is equivalent to giving an object f in the limit of the categories d of x to the I, where I is varying over what Dennis at some point called f set. So f set is the category of finite non-empty sets under surjections. So what I'm saying is every time you give me a finite non-empty set I give you a D module on x to the I. And every time you give me a surjection between two finite sets, then I'm supposed to give you an identification of the corresponding D modules. So that's what this limit means. And we can repackage this again. So this is the limit of some categories of D modules. So what that looks like is this is D modules on the pre-stack, which is the co-limit under I and f set and then up of x to the I. So this is a co-limit formed in pre-stack. And this thing goes by a name. Not surprisingly at this point, it's called Runspace. And this is, just to reemphasize it, it's defined to be the co-limit under I in f set up of x to the I, the co-limit having been formed in the category of pre-stacks. So this thing, at first pass, you might think that it's an in-scheme because what we're doing is we're taking these x to the i's and we're taking some co-limit under closed embeddings. Right? These diagonal morphisms are the relevant things. But it's not an in-scheme because you're supposed to take a filtered co-limit in that case. And this co-limit, unfortunately, isn't filtered. So it causes slight annoyances. It's something to be aware of. It's not a traditional object of algebraic geometry, which is part of why we like this generality of pre-stacks, is that it allows you to consider these kinds of
You
beasts. So
only need to know what what the sheaf on this object is, and you have just defined it before you define the object.
Actually, it's not true. So it just turns out that if you have Ran as a pre-stack, it's very, very handy.
Yeah. So.
Will you explain where?
So let me make one comment on it. So in fact, this pre-stack, okay, it's easy to describe. I'm going to describe its Derived space instead, just to make my life slightly easier, but it's not so serious.
So wait, so Derived space is easier to describe than the thing itself?
Slightly. So it's not a huge deal, but okay. So the pre-stack is going to be. So wait, let me write the formula and then we can talk. So the RAM? Wait, what? I'm.
You produce Run space of X the Ram, or vice versa. You produce Run space of X and then take the.
Also, they commute. So I'm writing it in this way because it's an unambiguous formula, but it doesn't matter. So the nice property is that the set of points of Run space are just finite subsets of maps from S reduced to X. So for example, if this is K, if S is spec K, then I'm saying that like the sort of physical points of Ran space are just finite subsets of the curve. So this is some weird algebra geometric object that exactly allows us, whoops, lost it. It exactly allows us to talk about sort of sheaves that are continuous, that are, okay. Sheaves on Ran space are exactly this kind of heuristic I was giving before of a continuous assignment of a vector space to every finite subset of the curve, and that is continuous with respect to just varying the points sort of in small ways and continuous with allowing them to collide. You're not allowed to split them off. So X can be anything. So the upshot of all of this is that factorization algebras define D modules on Ran space. And that is exactly equivalent to axiom 1. So that's what I got. It is a set. So it happens to be a set.
So can you still say what are S points of Ran?
Let me not do it now, because the answer will be, like the answer I will give you is going to be complicated, and it's inconvenient for the framework. In the classical case, it's the same. It doesn't. The reduced part doesn't matter. The problem is for derived, because I don't know what finite subsets of a groupoid are.
Derived S or derived X?
Derived S is when it's annoying.
And so
Yeah.
for classical,
It's just the same formula. It's just finite subsets of X of S. Yeah.
oh, so this pre-stack is not classical.
The pre-stack is classical.
The rest is classical.
Yes. But so what? Like, see, for a classical pre-stack, you can still talk about its derived points, and those are still important. Like, that's the cotangent complex. So.
But that's kind of algorithm. If you say it's classical, then somehow.
But the algorithm is extremely difficult to implement in practice. Yeah, it's unfeasible. So that's why we like.
It's just enough to write this formula for non-derived S and say that this is your definition.
It's enough, but you would burn in hell. Yeah. Any other questions?
So the data factorization is some extra data apart from, so it's a DMOD on Ran X.
Right, plus this extra data of these disjoint things. And again, it can be formulated entirely in terms of Ran space, actually. You don't need these powers of the curve. So whatever. Yeah, I mean, basically, you think disjoint subsets of the curve, you want the fibers of those disjoint subsets to be the tensor product of the fibers. So you can spell that out explicitly and do something. Other questions?
What happens with the maps? I mean, how you map finite subsets to finite subsets? Just the image?
Well, see, wait. OK, what maps between what?
I mean, you have map in S and S prime.
Yeah, so then it's given by restriction. So if I have, see, if I have a map, OK, you said, let me say S prime to S. So if I have a finite subset of S points of X, then I can restrict that to a finite subset of S prime points of X. And that's what the structure is as a pre-stack.
So is it a pre-stack in group weights?
It turns out to be a pre-stack in sets. For Ran X to Ram.
So not in group weights.
Also in group weights. Sets are particular examples. Other questions? Great.